So hello again. Tonight, we're going to be talking about if we did receive a signal from an extraterrestrial source, how would we know it? How would we decode it? And we'll consider that from the opposite point of view. Let's say we were sending a signal out into the deep space void. How would it be encoded such that somebody on the receiving end would need to know the following things in order to decode it? I think it's going to be a short one, unless I get into the weeds. I was watching a YouTube video by StarTalk by Neil deGrasse Tyson and Chuck Nice, and they were talking about, would extraterrestrials count the same way we do? You know, we have two hands, 5 fingers on each hand. That comes up to 10. Everybody on the planet, unless they've had a problem, counts that way, maybe using different symbols, but 5 and 5, 10. And so we all use the base 10 numbering system. Well, maybe that's not the case throughout the galaxy or the universe. And that got me to thinking about all the other things that we would have as unsuspecting earthling biases in our communications, that if we were to receive communication from an extraterrestrial source, they could have off-world unrecognized biases. So we have to pay attention to these things. It's not like it is in the movies where they just go, I know that's a video signal, just invert it and, oh, sounds like audio. It's a little more complicated than that. So we'll go through that stuff. As I said, counting. 2 hands, 5 and 5, 10. So we came up with digits 0 through 9. And yes, I am including 0 because that is 0, and that's 1. But, you know, we have 10, so we do 10. But that's only because we're efficient. We could have just as easily said, my hand was occupied, so we can count to 5. So it's 0, 1, 2, 3, 4, 5, 1, 0, 2, 3, 4, 5, 1, no, 2, 0, 2, 0, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5. So we could have done it base 5 and still counted successfully. But somebody figured out if we increase the number of counting positions, we can pack more data into the same set of digits. But let's say we're an extraterrestrial that does not have opposable thumbs. We've only got 8. We have octal. So now we have 0 through 7. That makes our numbering system different. And if we really want to bring down the efficiency, if I only counted on one hand, it would really bring it down. So now whenever I want to tell you a number, I have to map from our base 10 to whatever they're using, or from whatever they're using to our base 10. And that's assuming that they've got a certain number of digits and a certain number of arms, hands. What if we encountered an extraterrestrial species that was more like, I don't know, spiderish? They've got, more than 2 hands, and they've got fewer digits or more digits on each hand. So now the numbering system is really in need of a mapping before you're ever going to understand things. And then there's always that, we're still counting flat things in scalar. This is before we take into account 3-dimensional thinking, as it's discussed in Contact and Star Trek: The Wrath of Khan. But that's not how computers do it. Computers are like switches. They have 0, 1, off, on. So they count in binary, and then everything has to be grouped up beyond that. And when you're talking, well, what about quantum computers? They can have a probability value between 0 and 1 for any qubit. But that just means it can take on a value between 0 and 1. And how do you get the actual value to map that to the real world? Well, it goes through a little piece of electronic gadgetry called an analog to digital converter, and it takes that RF signal and evaluates it as a voltage in the range whatever the ADC converter's range is, and those are the numbers you get out of it. So they're stair steps. They may not be precisely continuous. It may just be, if you have a probability of 0.01, you get a number. And if you have a probability of 0.02, you get another number. Well, what about 0.015? Well, that's between the latter steps of the converter, so you don't have that. So even saying, well, it's quantum computer technology, that doesn't mean you aren't counting in digits. That just means you count differently. And how many steps, how many rungs on the ladder between the 0 and the 1, and that's variable. If you want to do it really high speed, you use fewer bits, fewer on and off switches. And if you do that, then you're not going to get as filled in a set of values, possible values. But now they're making the quantum computers with ADCs that are more than 8 bits. They're 10 bits or 12 bits, which is a somewhat improvement, but not that great. But in general, when computers, non-quantum types, are counting, they don't count in base 10. They can convert to base 10 or display things in base 10. But internally, since they're binary, it's more convenient to count in base 16. Well, how do you do that when you run out of digits after 9? Well, they just started using letters, A, B, C, D, E, F. So to get base 16, get your 16 values, it's 0 through 15. But we want to keep it as a single digit, so we go 9, A, B, C, D, E, F. So 9, 10, 11, 12, 13, 14, 15. Or as it's known by computer people, hexadecimal. And then you can glue that together in strings and come up with, it takes 4 on-off switches to encode those values. And so 4 bits gets you 1 hexadecimal digit. And if you want 2 of those, you get a byte. And then you can get more of them to like 16 bits, 32, 64 on a computers. You might hear discussions of computers being. So anyway, when you talk about computers being 64-bit, the 64-bit is not really meant for storing bigger numbers. It's really meant for storing more addresses, so you can have more RAM on your computer, more addressability. There was a time when characters stored on computers in bytes were not 8 bits. They were 9 bits, and you stored them 4 at a time in a 36-bit word, not 32 bits. That was a UNIVAC, or as it was later known as Sperry UNIVAC. And IBM pursued with, Intel behind them and others, the 8-bit and 32-bit world. But I also know there was some numerical analysis and scientific computers that were not 16 bits. They were 24 bits and 48 bits and 96 bits. So it's whatever your computer's designed for. But it all is based upon on and off, ones and zeros internally. So if I wanted to store a number, I need a certain number of bits to make it fit. And therefore, I need to store it in a nibble, a byte, a word, a long word, or a double word, or a quad word. And you can see how, as I add more bits to it, I can get a bigger number. I can store a bigger number. So when I'm communicating things and I want to say, here's a number based upon how big the number is means it's going to occupy more bits, more communications has to go out. And how do you know to decode all that stuff? Well, you need something on the outside that says, by the way, that's a 16-bit number. So when you're sending to extraterrestrials or when you're receiving from them, what's a word? What do their computers look like? What's the largest number they can fit in a word? And then for the scientific folks, or for the folks that deal with very big numbers or very small numbers, we have this thing called scientific notation, also somewhat known as floating point. And if you ever look at a number in like Excel and you see it scaled in scientific notation, you see there's 2 parts to it. there is the mantissa. That's the digits left of that, times 10 to the whatever. And then there's the 10 to the whatever. In computers, they don't do it times 10 to the whatever. They do it times 2 to the whatever, because computers are binary. So they have a different base, different radix. It's 2, not 10. And then how many bits of mantissa and exponent varies, but there's an international standard for floating point that says what these things are. So if you say, I've got a floating point number and it's in single precision and it fits in 32 bits, you've got 1 bit for a sign bit that says plus or minus. You've got 23 bits of mantissa, that's the stuff left of the, times 10 to the whatever. And then you've got 8 bits of exponent. Now, if I want more precision, I can up it. So if 23 bits doesn't give me a more accurate, doesn't give me all the decimal digits I want, then I can go up to double precision and get 52 bits. And if I don't need that much bigger a number, I just go to 11 bits of exponent. And you can see as I increase the total number of bits in the storage, I now have bigger and bigger numbers with higher and higher precision that I can store in the machine. So when you start communicating and you say, I want to communicate the number of light years and it's a really big number, or I want to communicate a quantum value and it's, nanometers, but I measure it in meters. So I need some way of representing these very small and very large numbers. But how do we get, words? Well, words are based upon characters, letters, special characters, numbers, digits, those kinds of things. How do we get that into the computer so that we can communicate it, or they send it? How do we pick it apart? Well, there's character sets. This is nationally recognized or internationally agreed standards for a value of hexadecimal 41. That's a capital A. Doesn't look like a capital A, but there's an international agreement that says if I store hex 41 in a byte and then I go to print it out on the display or on paper, that's a capital A. Well, that's great for us, Latin letter systems, including English and European, and Arabic and Slavic. But what about those symbolic countries? Well, they have their own national standards. So for Korea, they have 2. Japanese has 3. Chinese has 2. The Thai language has essentially 3. And for all of India and Nepal and sort of a couple of adjoining countries, they got together and agreed on just 1 character set. But there's an international standard called Unicode that can take any of these things. It's just, it's a very wide value. So instead of it being 8 bits per character, it can be multiple groups of 16 bits per character. So you can do a lot of different languages that way. And then we got to chuck in all the things we want to draw quickly. So if I want to draw those funny little characters at the bottom of a barcode when you go to buy a product, those are digits. But what about the bars themselves? Well, there's standard widths for those bars, and there's actually a character set for that called optical character recognition, or OCR. Well, that's one of them. Those funny letters at the bottom of your check? They used to be in magnetic ink. They're not in magnetic ink anymore. They're in just high contrast, optically readable ink. But the shapes of the letters, those funny little digits down there, all have to be precisely that for them to be able to be read very quickly. And that's called magnetic ink character recognition, or MICR. I used to run a MICR sorter. That's like when you get all the checks in and you have to sort them and find out what account's going to be drawn and that kind of thing. That's a MICR sorter. So I knew about all those little characters down there. But there's all sorts of very special ones for doing special things, like wingdings and webdings and various versions of that. They're just funny little pictures of things, not quite emojis or emoticons. Those are, even more complicated. Those are graphics. But whenever you want to communicate things and communicating from one earthling to another, these are the kinds of symbolic encodings you can have before you ever get to decoding the foreign language itself. It's the letters. Now that you can communicate the language, what about communicating other stuff? Pictures. You want to communicate snapshots, images of things. This is what Earth looks like. Or here's a video, watch Earth rotate. Here's some audio. I'll play for you all the sounds of the planet, like certain golden disc records have on them. So, they could say, from the people of Earth, here's what we all sound like. No, you sound like ones and zeros. I need to know what the encoding is to be able to play that back such that it sounds like that. So there's audio encoding formats. There's a whole bunch of them. And all these things have open standards, and then they have proprietary versions of all those things. Okay, now you can do images and animation and audio. What about more complicated things? What about 3D models? I want to send a 3D model of an electronic gadget to somebody out there who's going to build one, and that tells them how to communicate with us. How do I tell them this is the object? If I just take a picture of it, that doesn't give you dimensions. But if I have an object model of it, now I've got all the angles, sides, materials, and dimensions. But I have to have a standard for encoding all that stuff so you know it. There's 3D modeling standards. How about buildings? I want to describe what a 20-story building is. I need an architectural standard for communicating that. Luckily, things like, Autodesk, AutoCAD has standards for communicating architecture and schematic things. But there are also standards for circuit boards or printed circuit board PCB layouts. So if I wanted to say, here's how to build the electronic transmitter to get to us, I need to tell them how to do that. So I need a way of encoding that so a transistor goes here, a resistor goes here, a capacitor goes here, a coil goes here, a switch goes here, those kind of things. So I need to communicate that. And there are open standards for that stuff, as well as proprietary versions. And then you said, well, okay, now that I've told you how to build the hardware, I want to teach you how to program the computer you just built. Programming languages. There's machine languages. Different computers have different machine languages. And then layered on top of that are higher level languages. So if I want to communicate, hey, build this widget, and now you can run this software and we can talk to each other. I don't know that their programming languages are going to be the same as ours. And then if you said, here's your build of materials, here's your list of parts, and here's, what the part number is and such. I'm going to send you an Excel spreadsheet. What the hell is an Excel spreadsheet? More encoding. So all of this encoding needs to be decoded. Now that you've communicated how to build and program the widget to interact with them, and you said, okay, I'm going to send you an appointment. I need for you to be at this location on this date and time. What's a date and time? If it's an extraterrestrial planet in a different solar system, their planet may be a different diameter. It may rotate faster or slower. Their day length may be different. They may be locked where it's always daylight on one side and darkness on the other. So time doesn't really change for them based upon, daylight and darkness. 12 or 24 hours. Well, the 12 or 24 is about our planet. If your planet goes faster or slower in its rotation, those are not going to be the numbers. What are your numbers? How do we map to that? Okay, now that we know when, where? Well, I'm going to give you the latitude and longitude. What's that? Well, it's measured in hours, minutes, and seconds for one of them and degrees, minutes, and seconds for the other. Well, why are they different? Just because if you get into some of the more serious astronomy stuff, they're both measured in degrees, minutes, and seconds. And you have to map hours, minutes, and seconds to degrees, minutes, and seconds in order to get galactic coordinates. So if they want to tell us where they are, then they're going to send it to us in galactic coordinates, and we're going to have to be smart enough to know that and map it onto our normal celestial coordinates, which right ascension is in hours, minutes, and seconds. And then you've said, okay, now we've defined all the stuff that goes in the meetup appointment. I'm going to send you the appointment. Well, there's a number of different things in the appointment. How do I know which one's which? Well, there's a data encoding format that says, like, this is the date, this is the time, this is the location, this is the distance you're going to need to travel. And there's a format for that. And there's two standards for it. And they're both internationally recognized. One's called ICS and one's called VCS. And you can tell V stands for variable. So it can have a bunch of other things. Now that you've got your data and you want to send it, well, ones and zeros are how the computer stores it. But you can't just switch a signal off and on and have it go out into deep space and then be detectable from a distance, because there's all kinds of noise bursts out there that can saturate your signal and attenuate it. And you need to put modulation around it. You need to have a carrier that's like an always on tone. And then you switch the tone off and on, either just in amplitude, in voltage, or how quickly you wiggle it in frequency, or maybe you phase shift it. And that's the three things you do to your carrier, your tone, in order to say, that's a 1 bit, that's a 0 bit, or if I do this with the amplitude, this with the frequency, and this with the phase, that's a trellis encoding of, like, 0 through 63. So now I've got to map my data bits onto that range and pack it all together. But then I got to add extra data for my error detection and error correction. In case there's a noise burst, I need to recover the data. Or if I send it, I need to include that error detection and error correction information with the data so that the receiver on the other end, some extraterrestrial, can go, I didn't quite get that. Well, you're going to wait for him to say, I didn't quite get that before he sends it again? No, you have to on the fly be able to decode with error correction to recover the data without having to ask for it to be resent. And you're going to be transmitting that on a certain wave frequency range, a band. Well, if they're not listening on that band, or we're not listening on that band, the tree fell in the woods and nobody heard it. Also, if we send the signal out after a certain amount of interference from things in the universe, it's going to get a weaker and weaker and weaker, and it's going to be chipped away, and the amplitude is going to be low. If the amplitude is too low and your amplifier can't lock on and detect the signal before it ever demodulates it, then didn't see anything. Same's true for the other end. If you send it out and they're just too far away, signal's going to be too weak. So you have to have a big enough ear, send or receive, big enough antenna, and you've got to have, those liquid helium-cooled amplifiers, the low noise amplifiers for your receiver, in order to detect that 1/1000th of a watt signal that's coming in. Because if you don't have that, I hear nothing. So what's my point here? My point here is that it's a lot more difficult to successfully communicate from us to them or them to us than just you speak at them. Okay, let's say I'm speaking over a microphone. How do I get my voice modulated onto the radio wave to send them? If they do the same thing back to us, even if I can successfully demodulate it, what about the language? What if we get started talking about counting things, and what's your counting numbering system? And so all of these things have to be figured out before we can successfully interact with one another. So, non-trivial stuff. And it's not like it is in the movies where they sent us the signal, looks like video, and then the video has an audio carrier, and we just decode all that stuff. Look, engineering blueprints, and we can build the warp speed space travel system. And that's good for the movies, but in reality, it's a lot more than that. Currently, with our current technology, we'd be lucky to detect just unusual, potentially synthetic patterns in deep space noise. If you've ever heard of the phrase counting on the kindness of others, if there are extraterrestrials out there and they're no more advanced than us, then both the sender and receiver of information suffers through all these data decoding and encoding issues on both ends. So that reduces the likelihood of successfully communicating. But let's say they're more advanced. If they're more advanced, they're going to have a much deeper realm of encoding to transmit more with greater efficiency over longer distances than we could ever think possible, at least by our current technology. So if they want to send us something like, hey, I'm going to be on your planet next Thursday at 3 p.m. Eastern time. Oh, yeah, Eastern Standard Time. And I'll be outside the subway station, number 6 in New York. That's the G train. If they want to communicate all that to us, it would be very helpful if they would translate all their more advanced stuff down to our dumber means of advanced communications and locating things, so us silly humans can receive it easily and know where to go. Because if the message comes across and we don't decode it properly, they'll be standing there all alone going, I don't know where they are. I guess there's no intelligent life on this planet. Certainly couldn't decode something as simple as that. Any child, any school kid could do that on our planet. So we use a lot of advanced technology, but it's not been advanced for all that long. Here's a piece of information that you can probably ponder. We've been only doing radio frequency modulation for about 120 years. So you go back to like the early Marconi stuff and the Edison stuff, and when did we first encode a signal as opposed to just speaking and doing amplitude modulation of a voice? About 120 years ago. And we're still using the same stuff. So it's still mixtures of amplitude, frequency, and phase modulation, and everything's encoding on top of that. However, if you think back over the much longer history of the human species on this planet, hey, we were modulating smoke signals for hundreds to potentially thousands of years longer than that. So we're happy to be, using radio frequency modulated communications these days as if it's something advanced, and it's only 120 years old. Imagine if, let's say, the extraterrestrials were orbiting an orange dwarf star that has been around for 400 million years longer than our sun. Imagine what their communications technology would be like with just 10 million years advanced technology. They may have given up on radio frequency modulation. That's so slow. That travels at not more than light speed. And you just have binary? Oh, we gave up on binary a long time ago. We were way past quantum computers. And we used, much wider analog to digital converters that cracks out of a single qubit, maybe 4 billion possible values, not 256. So I'm hoping that they will take pity upon us dumb humans and encode their much more intelligent and efficient information into our more archaic RF modulation. And if you have to tell us to be somewhere by a certain time, make sure it's not, out in the middle of nowhere, because then we may have to arrange transportation. And, if you said, oh, we received the message in New York City and we need to be in the outback in Australia tomorrow, we're going to have to send somebody local because we can't get there with our commercial airplanes in that time frame. So, like I said, maybe it's better if they tell us to meet them at a subway station in New York City. So communication of complex things over long distances is far more involved, lots more minutia than just two tin cans with a wire between them. Our radio telescopes have to be sufficiently capable of receiving weak signals and then demodulating them. And then, if you think about what we sent out, hoping the universe would be able to easily decode it, that was the block pixel characters SETI sent from Arecibo. Haven't heard any word back yet. Maybe it was just too simple. They went, are they that dumb? I don't want to talk to them. And then consider all the language and data and times and distances and coordinates and all that kind of stuff. And then the languages. All that stuff has to be demodulated and decoded before we can ever talk about. They sent us a paragraph on, a cookbook. And RF communication, while it's gone a long way for us, it may not be the end all of communications. They may be using, neutrino modulation or gravity wave modulation for a more reliable signal. But I think in essence, it comes down to don't attempt to call them. Wait for them to call us and hope they take pity on us and will call us in our own vernacular. In the meantime, it's not going to hurt to try and talk to them, but just realize that if you did get a signal right now, you may not be able to recognize it or decode it. And there's the StarTalk video on YouTube. And then if you want to get into the minutia, I've got links. All kinds of computer stuff. Radio frequency modulation techniques. How to encode graphics, video, audio, 3D models. A historic list of computer programming languages and how few of them are still in use these days. But COBOL's still around, Fortran's still around. And then if you wanted to communicate coordinates of something on Earth, it's called geodetic coordinates. When you go to the moon or some other planet like Mars, you need a different coordinate system. Okay. I thought that would be a fun filler, about an hour long.
Yeah.
So I know the people that are somewhat computer literate, if they don't use it on a regular basis, it clicked a pain in the back of their mind, I'm sure. Oh yeah, all that base 16 crap. I haven't heard the word
mantissa since college.
yes. Mantissa and exponent, yeah.
Yeah.
I do data encoding on Raspberry Pi, so I have to be savvy in how Linux does it different than Windows.
Mm-hmm.
And medical device interoperability. I did not in any of that discuss units of measure. Whenever you're communicating with medical devices to clinicians, you not only say, it's 12. 12 what? It's 12 milligrams. Oh, okay. So it's not only the value, it's the units of measure to go with the value. And if you think about it for a moment, even spreadsheet tools that you use, there's no direct capability for units of measure. When you put a number in a cell in a spreadsheet, it's just a number. Wouldn't it be nice if you could say, it's a number and it's this units? So that if you wanted to say, I need to convert microns and nanometers, you could just store the values or add the values and it would automatically calculate them. But you know what it does that for? Time and date. If you said, how many hours between last Thursday and right now? Most computer systems and programming languages have the ability to just subtract this date from that date. Look, that many hours. But when you talk about other things like meters versus millimeters versus nanometers and microns or angstroms, different units of measure, you got to roll that on your own every time you need it. Now you can get libraries that will do that stuff. You can even get online tools or cloud-based tools for converting languages, human spoken languages, but not that many opportunities for saying, I've got a program written in C++. Could you please translate that to Python? Well, there's some tools that'll take a good shot at it, but not give you a reliable conversion. So did I miss anything? I know.
A lot to think about, and like for time, for determining duration, you'd probably have to go with the vibration of a cesium atom or something like that. But then you have to identify the atom.
Yes.
How do you tell them what it is? Yeah.
Well, you have to tell them, well, how many protons does it have? Oh,
yeah.
I have to communicate a number. How do I communicate a number when their world is octal and our world is decimal?
Yeah.
How do I know that? Well, somewhere I have to say it's an 8 or a 10. What's an 8? What's a 10?
Well,
what's an atom? How would their visualization of an atom could be different from ours.
Well, even ours has changed over time.
Yes.
We used to start with the Bohr model, and the Bohr model was just spherical shells.
Right.
And now that we have deterministic things, we can actually see that there's a probability of where the electron is going to be. And depending upon the level number, it's not spherical sometimes. Sometimes it's donut shaped. Sometimes it's toroid shaped. So, yeah.
One thing is sure, we have to wait for them to communicate.
That's the whole point of this thing is, this is complicated, and theirs is likely to be different from ours. Let's hope they're far more sophisticated than us, and they can dumb down and learn our stuff and then communicate to us in something we can readily, uptake.
Sure. They have billions of years ahead of us, so they have plenty of time.
I would settle if they only had 1 or 2 million years ahead of us. Because remember, 1 million years ago, we were roaming around in caves.
Where did there? Nothing.
So I saw a video this week on classifications of old ages. Like when you talk about Neolithic and pre-pottery and those kinds of things.
Yeah.
I found that in Turkey, there are sites where, well, they didn't make cooking vessels, but they made drinking vessels. But they didn't make them out of ceramics. They made them out of calcium carbonates.
Oh, interesting.
They look like pottery.
Mm.
They look like mugs, but have no handles.
Right.
They're mostly white because they're calcium carbonate. They found a way to take calcium carbonate from, you cooked up your dinner made of animal bits and you ashed up all the bones, and now you have calcium carbonate, and you mix that with certain things. And look, if you just let it dry out, it gets hard. Well, what if you took that calcium carbonate while it was still kind of soft, had some water in it, and then you shaped it into something you can drink out of, and then you left it out in the sun for a few days, and it got hardened. Look at that. And then the more interesting thing was they found out that if you maybe not, kiln flamed it, but you just heated it, you could mix in other agents that would actually harden it. And now you could put water in it and it wouldn't leak or dissolve.
Yeah.
So now they're trying to figure out, well, we know that this society was actually about 3,000 years older than what we used to call pre-pottery. So now they've got pre-pottery A, B, and C, and they found one even that had the calcium carbonate advanced pottery, And they had to give it like, well, it's the final C because they don't think anything can go back further. Foolish humans.
Yeah.
When they started assigning magnitudes of brightness to things in the sky, they said, nothing could ever be brighter than that. We'll make those negative numbers like the sun, the moon, but we know things can get dimmer. And as we advance our technology and make bigger and bigger telescopes, we can see dimmer and dimmer things. So the dimmer numbers can get larger. Well, whoever's doing the archaeological digs hasn't figured that out yet. We're going to start with A and go to B and then go to C. Any other direction. So what do we get if we've got one that's older than A? Negative A? I don't know what you call it. Pre-A? So they found that they were storing grain. How do you store grain that you aren't into agriculture? You're not farming, but you've got grain, and you could see that they were storing grain in these rooms specially designed for storing grain so the grain wouldn't rot. You know, mold wouldn't build up and the grain would stay dry and wouldn't rot. Pre-agricultural. So now you've got a pre-pottery, pre-agricultural society that is growing grain, but they're not farmers. And they're making pottery, but it's not ceramics. So, you know, every time we think there's nothing more sophisticated if we go further back, they're all living in caves. Not necessarily. So, yeah, we have a lot to learn about a lot to learn.
Yeah. It's scary even if we try to think.
Not scary. It's just a realization of we think we're advanced and we're just working our way through as best as we can. And if something new comes along, you know, don't let it unsettle your world. Just think of it as a broader picture. And if you have evidence of it and you've got proven facts, change is change. Okay. Any other comments or questions before I stop recording? Hearing nothing.